what I want to do is to talk to you about some of the ESD challenges in semiconductor integration as the content of semiconductors increases and the content of electronic systems increases in our daily life. The material here today is broadly based on material that's been developed in the Education Committee of the ESDA. And I will give a little bit of background on that as we come to the end of the talk. So to start, what ESD seems like a very unworldly event. So I want to bring it back to something we can all relate to. And I think we're all familiar with the dark clouds brewing on the horizon and lightning storm in our future, storm brewing ahead. This picture is taken from my hometown in Ireland. This is Sligo Bay with the iconic Knocknarea in the background. And we're on the very northwest coast of Ireland, facing out onto the Atlantic. So these storms are a very frequent occurrence. Lightning is one of the most commonly understood electrostatic buildup and discharge mechanisms because it's so visible to us and it's been studied for a long time. The buildup of the static charge in the clouds that then discharges to ground. Just to give you an idea as to the magnitudes, the typical magnitudes of voltage and current. In an average electrical storm, discharge to ground, the typical voltage levels will exceed a megavolt. The current levels will exceed tens of kiloamperes, and the discharge time is in the hundreds of milliseconds. And needless to say, this can be very destructive. So then when we talk about designing electronic systems or systems to survive lightning transients, this is work that's been done since we started deploying electronic systems in our environment. The best strategy is to divert the transient away from the system. So schematically, we can see here a lightning event which will induce a transient. That large transient could be quite a significant energy event. Is diverted to ground through primary protection. So it's primary protection outside of the system. This is something that's been deployed and used, particularly with power and telecommunication systems. In this case, something like a T1 transceiver. So the energy is diverted to ground through the primary protection, but there is some energy that's let through, some lesser energy. And that is dealt with through secondary protection. So on the circuit board, there's line side protection, transformer, and IC side protection. So the overshoot, the transient overshoot, is minimized through every part of the protection, such that when the transient reaches the sensitive CMOS circuit, it's at a safe level. So, from a very large event to a very manageable transient, the primary protection, secondary protection system works. So, and this is the concept that I'm going to come back to throughout the talk. So electrostatic discharge, it's not lightning. So what is it? It is something that we are also all familiar with in our everyday lives. It's a real world event. Whether it's walking across a carpet in a casino in Las Vegas, or sliding into the car and then stepping out of our car, touching the metal frame, we've often felt the discharge event, or just discharging to a metal object like a door handle. So these static electricity is all around us. If you feel this event, it's in the range of plus minus 8,000 volts or higher. This is, of course, orders of magnitude less than a lightning event. It's also much less in terms of the amount of current and much, much shorter. It's in the nanosecond time domain. And it's completely harmless to human skin, or harmless to us. But these numbers, I think 8,000 volts, not quite so harmful or not quite so benign to electronic systems. So this is really the world that we live in. There's a lot of static electricity events and discharge events all the time, of which we are immune to, but we need to take care of when we talk about electronics. So in terms of what is triboelectric, triboelectric charging, this is something that has been studied for, I would say, about 3,000 years, perhaps. The first serious study was done by a Greek philosopher, Thales of Miletus, about 500 BC. And that was really the study of how an object can gain electric charge, gain charge by coming into contact and then separation. So when two objects come into contact and then subsequently separate, when one of those objects becomes charged, that is triboelectric charging. The subsequent discharge, when that charged object discharges to a ground or something of a different potential, this is where the destructive event happens. So the charging does not cause damage, but the discharging is where we see that rapid single event, rapid transfer of energy, where you might feel a spark. So this rapid discharge of energy where you see sparks, that became an area of study in the time of the Industrial Revolution. And one of the, many different areas became impacted, but one of the most relatable was the paper mills. So rolling paper onto the drums created built up a lot of static electricity, and making sure that the industrial controls were in place to prevent that discharge leading to fires or other problems became an area of study in the late in the 1800s. So how this happens, how this triboelectric effect happens, and how different materials are related to each other, it's not that intuitive. So it does require study. And the first triboelectric series, which lists materials in terms of their more positive tendency to become more positive or tendency to become more negative when they come in contact with each other. This triboelectric series was first published by a Swedish scientist about 200 years ago. It's been maintained and refined and added to since then. We can look to see how we might interpret this. Like the human hair, I'm sure we've all had experiences, especially when you're in an area of low humidity. So when it's very dry, a plastic comb through your hair can easily start out your day with a very bad hair day. So the human hair is on the more positive side of the triboelectric series, and plastic is on the more negative side. And this results in the charging effect. We can also see this in a more sympathetic way when polystyrene on a cat fur shows the charging effect of the, again, triboelectric series, and the charging effect between the cat having a playful roll around with the polystyrene. So up to now, I really wanted to introduce the concept of ESD discharge and static electricity being everywhere and an everyday event. Non-destructive, not a problem for us. But when we translate this into electronic systems, it can be a problem. So in the industry, we have over many years and lots of different standards bodies identified models that replicate the discharge in different environments. So we have, I'm highlighting really two different environments here. What I call the IC level, so this level down here, which our target for standards, and I'll go into reasons why, is in and around 2000 volts, and it's called human body model. So 2000 volts human body model is a level that we, in and around this is a general statement, is a level that we target for ICs to withstand. And there are test methods and models associated with both designing for and testing and guaranteeing the compliance with those levels. But in the end system, the models reflect a much higher level of dissipation. So the levels in the red and the blue curves represent plus minus, or well, plus in this case, 8,000 volts, which if you remember is back in the order of what you feel. If you can feel a discharge event, then it's in and around that level. So this 8,000 volts is a model that represents that type of discharge, given different types of Rs and Cs and whatnot. It also corresponds to a peak currents. So the peak current here is in the the 30 to 40 perhaps amps at this first peak. So this is just to give you some context as to real world static that you can feel every day. And this relates to how we're going to protect the electronic components. So first off, why is there a difference between the IC and the system? So the ICs represented here, a little package, the ESD control, ESD levels that we build in and design our ICs for assume that the IC is only ever going to be handled on its own in a static controlled environment. So there's measures put in place to control the static, the maximum amount of buildup of charge inside a static controlled environment. And then we can design for protection at levels below that. So our IC, if it's designed to meet 2000 volts, it means that the low level static buildup that's inevitable, that's going to happen because of movement around, will be safe for this chip. But that the static control guarantees there will not be any stress in excess of that, right? So how do we get that level of control? Because that's really a key thing. We're assuming that our static control prevents any excess damage happening, and we design just to make sure that that low level is not a danger. So the first, the representation here of an engineer at his test bench, the very first control that's put in place is grounding. And this is a cartoon representation, but these basics are seen across all of our factories, test houses, assembly houses. Grounding is the key and the very first, the most basic level of ESD control. So wearing a wrist strap or grounded flooring or footwear or furniture is the first level to make sure that the engineer, the body, doesn't build up too much potential and then discharge it into the poor IC. Second order is a grounded work surface. Similar idea. If you're going to be placing objects on the work surface, you don't want the work surface to be at a different potential. And thirdly, as we're handling the sensitive objects, they need to be placed in protective packaging, like a Faraday cage around the sensitive object, so that as it moves through the factory or as it is shipped around the place, there's no way that it can get affected by any static discharge. So this is how ESD is controlled in a production area in a very simple 3 steps. Of course, there's a huge body of work that studies this and implements these controls in all our factories today. I thought I would just share a little of the outside of static controlled area. Here we are in Santa Clara County, sheltering in place, and an impromptu workbench has been set up in our kitchen, and not a grounding strap or ESD control method in place in sight. So I'm not sure how the project is actually going to turn out, but one of the primary goals of my being here today, and one of the missions of the ESD Association, is to improve understanding and awareness of static. And I think we can start at the high school level to help our future engineers understand the importance of control. Okay, so in general, the last slide accepted, the IC, the assembly, and the assembly into the final system is done in a static controlled environment. But in reality, we walk around in the real world and we hold on to and touch and interact with these electronic systems all the time. We're not wearing wrist straps. So we know that we need to build in a small level of ESD protection at the IC level, but the end system needs to be able to withstand much higher levels of ESD protection. Similar to the idea of lightning, the primary protection, the secondary protection, and then minimize the impact on the sensitive components. And so I'll mention a little bit about how that's done, but first I want you to, Samsung being one of the key providers of electronic systems, of course, very much aware of compliance testing. So when we as consumers buy something, whether it's electronics, medical electronics, automobile or whatever, this has already been, the electronic system has already been tested and meets compliance standards. And those compliance standards also include ESD immunity. So we know that if we see the CE mark, for example, this is just one example of a compliance mark, that it has already passed the required immunity standards, so that we don't have to worry about wearing a wrist strap when we answer our cell phone, to put things simply. How is it tested? So again, this is tested with a system that replicates a discharge. In this, we call it an ESD gun. So the ESD gun is used to discharge to different points in the system. In this case, there's a grid. The testing would follow a grid pattern, looking for catastrophic damage due to the discharge, or maybe just flicker on the display, a reset, something like that. So when the part is qualified and it meets compliance, it means it's been tested. It includes the fact that it's been tested to meet these IEC ESD type system requirements. So having this testing, having a gun replicate the testing and seeing what levels to do it at, is it really a threat to electronics? I mean, we often get questioned about are we being over conservative? Is this realistic? What's the right number? Is it 8,000? Is it 10,000? What is the right number? So Michael Heaney, a physicist at Amazon, he has given several really very good talks at the Bay Area ESD Association meetings, and kindly agreed to let me share the results here. This is a fascinating study that Michael undertook in order to benchmark what are the levels of ESD that he can measure on a person. So what he did was he took an ESD meter to measure the voltages on a person, and that person was generating the voltages by putting on his fleece jacket and just rubbing the fleece jacket and then taking off the fleece jacket. So the person was being charged by this interaction with the fleece jacket, let's say. And it really depended on the relative humidity. As we know, relative humidity has a huge impact on ESD discharge. You never feel the spark in the middle of the winter, or at least not in Ireland when it's raining all the time. But in Arizona or in a very dry environment, you'll feel sparks much more. In Las Vegas, for example. But okay, getting back to Michael's study. So what he measured was at low relative humidity, so down about 10%, the red dots are actual data that was measured on a person. He could measure 20,000 volts with low relative humidity. As the relative humidity increased up to like 70%, or well, okay, let's say 60%, the maximum he was able to read was more like 4,000 volts. So this gives us a benchmark and shows that yes, these numbers are real, and the levels, although maybe the higher levels are more extreme depending on environment, these are something to pay attention to. The other part of what Michael did was he looked at a typical handheld electronics device, an e-reader, tablet, or smartphone, and looked to see what parts of the phone or object that are the electronic device are we most likely to discharge to. So combining the two, he was able to define, this is what we need to do in order to make sure that our products are safe. So this is a very nice study that was done and presented. Overall, the integration of electronics in our everyday world is increasing at a rate that is hard to even comprehend. But in terms of what is, the difference between building in ESD protection for a ESD controlled environment versus allowing getting access to that system in our everyday lives. Sensors are one of the area where, because the sensor itself must interact with the outside world, then it poses another layer of challenge in protecting for ESD. And I'm thinking of areas like magnetic sensors, humidity sensors, temp sensors, current sensing. These are becoming ubiquitous in our everyday lives, and as the sensor element is integrated more with the IC and with the semiconductors, the ESD protection also has to be built in. It really does blur the lines between inside the chip and outside the chip. Taking that into the application, we see an increasing semiconductor integration and intelligence as manifested itself in the Internet of Things. So if we think of all of the common features of some of the Internet of Things applications, like low power, wireless communication, sensor integration, distributed analytics, need to work in harsh environments, lots of new types of package types, etc., and of course built-in security. All of these features impact the way in which we think about ESD protection. Low leakage, low capacitance, immunity to other not interfering, ESD and EMC not interfering, etc. So these are all things that keep our job more and more interesting. There are always new problems to solve. When I look back and see, in terms of increasing electronic complexity, an interesting benchmark is the automobile. In 1950, Chrysler incorporated the first all-transistor car radio. So this was the first kind of notable electronics included in a car. In 2020, an average car would have something north of 5,000 semiconductor elements, 200 electrical devices, and 85 ECUs, electronic control units. In addition, connecting all that together in one vehicle, you could have 3.5 kilometers of cable harness and also a bunch of software that's controlling and needs to be controlled. So let's look at that in another way, right? From 1950 to 2020, the average cost of electronics as a percentage of the cost of the vehicle has gone from 1% to 35% in 2020 and is only going upwards. So I think this to me is quite phenomenal. Just the average electronics cost as a percentage of the total vehicle cost. So of course, it's becoming important to make sure that, as with all our robustness testing, that the electronics in the vehicle are also immune to static discharge events. Now, I'm going to date this picture significantly. You can see that there's a key in the car, and in fact even a button here. This is clearly not the most recent photograph, but the idea here is just to show that, similar to the gun testing with the handheld electronics, the vehicle is also tested in the same way. So every part of the vehicle is tested to make sure that the electronics don't either get destroyed or respond incorrectly if they get zapped by discharge. So getting back to our, relating back to the idea of lightning transients being protected with primary and secondary protection in order to keep the high disturbance away from the sensitive circuit. Similarly, for system level ESD protection, in this case, if we had a circuit system, if you imagine, where there's a connector that connects into the system, and I come and touch the connector, discharge with plug in the connector, but in the act of doing that, I discharge some ESD event to the system. This could be quite catastrophic. So what we have in building in our systems, we include this primary protection, which will ensure that the discharge gets shunted to ground and shunted away from the system that we're trying to connect to. So this is essentially the same idea as the lightning. This is an example. So coming back to the automotive example again. So building in that type of protection, sometimes it can be built in at board level, sometimes it's built in at IC level. So this is an example where inside of an automobile, there's a serializer, a deserializer, going from a controller out to a speaker or to a video display. And they're both connected together with a long cable. So the cable has connectors that connect to the ICs. And of course, it's a high-speed link, so we don't want a lot of parasitics, etc. But in the vehicle, we've identified that the points that are sensitive to discharge are here at the connectors. So the ICs need to be designed with that, the ability to shunt the transient to ground on the chip. So it's more than just handling in a static controlled environment. In this case, the IC has built in this sort of large system level discharge protection event or capability. This is how we test to make sure. So ideally, in the end of the day, you need to test the vehicle to make sure the vehicle is safe and doesn't get disturbed by any of the ESD events. But we don't want to wait until the very end to make sure that that's the case. Every subsystem, as it's built up, every subsystem will get tested. So in this case, based on the previous example of the communications chip inside the vehicle, there's a little evaluation board built up. And this is just for demonstration, but the IC is placed in here and hooked up to a controller. And we bring the discharge gun. You can see the little zap to the discharge gun. This will test the IC in this environment before it gets built into the ECU or whatever. So just an example here of how the testing goes from system down to subsystem down to IC level. Okay, so at IC level, how do we actually do this? What is it? So ideal ESD protection, it really is and should be invisible to the circuit. In normal operation, the ESD clamp is open, and under ESD stress, it's short. So the ESD event is discharged away, but when there's no ESD, it's invisible. And this ESD protection is required between every 2 pins on the IC, because the ESD stress is indiscriminate. So I'm going to give you maybe a little bit of my frustration, or maybe not frustration, but in some of our very technical publications, for example, here, ISSCC 2020, this was actually held in San Francisco in February this year. I think it might have been one of the last conferences before we went into shutdown. But at the conference, TI had several presentations, but one of the presentations was a 16 nanometer new IC, a platform for automotive and embedded applications with integrated safety MCU. And really, this paper detailed out some of the best work and showcased the best work from this group in TI. And I think it's fair to say that I should go back and revise history a little bit and add in, along with the other excellent work, the ESD portion that we know is there but gets forgotten because it doesn't, in the end of the day, this new chip and any new chip or any new system that we design and build and sell, we're not selling it. Nobody's going to buy it because of its ESD protection. That's a given. It just needs to be, it needs to survive, right? You need to be able to build it. But nonetheless, as an ESD person, I wish they would add in the ESD part of this, because it does consume a significant portion of silicon area. An average IC, the ESD protection can be anything from 5% to 20% of the IC real estate. So that this is a highly integrated digital 16 nanometer design. And here's another example of another IC from TI. This is a flux gate, integrated flux gate for current sensing applications. And this chip or this technology and paper was presented by my colleague, Dakwon Lee, who sits very close to me actually in TI. And again, I have to revise history and say, hey dude, don't forget the ESD. We want to add that in. So, okay, enough. I don't think I need to reiterate that the designers and design community, the marketing guys, the system sales, etc., they're not going to prioritize ESD, but we do need to pay attention to it. And there are specs to design too. And most important is to understand the impact of the circuit. So we want to make sure that the ESD protection we add in, which is on every pin, doesn't affect the performance. So things like leakage, capacitive loading, inrush current, latch up are all aspects that we have to pay attention to. And it requires planning in advance. So even though the designers might not want to, we help them understand the importance. And this is also part of the work that we're doing today. I'm going to touch on just one or two little aspects of ESD protection. We look at ESD devices in different ways, or we look at at silicon devices and components in a different way than normal circuit designers. So when you look at a MOSFET, for example, the normal care-abouts of a MOSFET relate to controlling the gate so that the switch is on or off, the drain current is high or low. When an ESD engineer looks at a MOSFET, they see the parasitics. And in any MOSFET, there's also a parasitic bipolar. And if we can leverage the parasitic bipolar, then in the same area, we can use that to conduct much higher ESD current than if we were just using the MOS. So the basic understanding of how parasitics work and how to leverage them safely is a very big part of the ESD engineer's job. It's been the subject of, conferences and papers over the last 20 years or 30 years even, how to better understand, control, predict, model the parasitics that respond under ESD conditions. So the other feature here is that in an ESD condition, the discharge event is very fast. It's a sudden event. It's a short duration event, very high current, and the voltage is clamped actually by the device itself. But it's not like a repeated event that you're going to see continuously every cycle while you're operating the device. It's an unlucky event, but you have to plan for it. So the behavior of the device and the modeling is more in a very short time domain rather than a 10-year lifetime consideration. Because of that uniqueness of the short, sharp duration and high current, there's also specialized equipment to help us characterize components and provide models under ESD stress. The most common used is a transmission line pulse, where we use a transmission line of a given length. The length then would relate to the length of the pulse. So different transmission lines are used for different pulse widths. But the most commonly used length is gives rise to 100 nanosecond pulse. So the method of characterization is to charge the transmission line, discharge through the device under test, and extract waveforms that then extract a quasi-static IV curve, or at least the first point. Then we redo the charging at a higher level, extract another point. Redo the pulse again, extract another, and continue going until we've reached the destruction point of the device. And then we, with enough points, you can join them together and say, this is what our quasi-static IV curve is like. So it's like a pulsed curve tracer. And this is really the foundation of a lot of the ESD design work. So we get a curve that looks in measurement that looks something like this, where we have milliamps per micron in a device width. We test to a trigger point. You see how much current you can carry safely, and then you reach a point of thermal failure, and you set the design guidelines so that you back off that and ensure that the designer doesn't reach that point. The point of failure is it's a thermal failure. So at some point you reach the level where the silicon will melt locally and low resistance path forms, causing permanent damage. So how are the chips designed for IC protection? I mean, this is not this is not intended for any design advice. Just in terms of concepts, between every two pins, we need to have defined a safe ESD path. So if we look at, for example, at an input pair, the input pair would have an ESD strategy that ensures there's a path between the input pair and the VDD and the input pair and ground. The typical damage that we see at the input device would be something like a gate oxide pinhole. So this is what we want to prevent. And the typical damage at an output device is a source drain damage. And this is also what we want to prevent. So the different mechanisms rely on current steering the ESD current away from the sensitive circuit and clamping the voltage at with an appropriate clamp. So this is using a rail-based scheme where we use diodes to steer the current and then the rail clamp to clamp the voltage. We also have to look from domain to domain. So on a large chip, we may have many different power domains. So even though the ground sound in the system, the ground is the same, on the chip, the grounds can be different. So we need to make sure that there's safe, low resistance ESD paths between every pin, even ground pins, and that every, from the output pin to the opposite side of the chip, we have defined a safe path. Moving from the IC to the PCB, I mentioned this earlier, I'm just going to mention it again. The second stage protection using primary protection using an external TVS or a capacitor or resistor is very important in protecting, in reducing the burden on the IC. The IC doesn't have to take all of the hit of the external event, and instead the primary protection will do that. Again, going back to the idea of the lightning strike primary and secondary protection. So there's a lot of different approaches here, but the concepts are very similar. So just to give some common strategies. Oops, maybe I went a bit too far there. Oh, anyway, some common strategies. We can have, most systems will have the external protection on the PCB board, this primary protection that relieves the pressure on the IC. But sometimes, like for example in the serializer, deserializer chip I mentioned earlier, because of the way in which the system is set up, the system level, the very high level of ESD protection has to be built into the chip. It comes at a cost because you're allowing the energy to get into the chip, whereas really we want to keep it away from the chip. But both ways can be made to work. Selection of one of the board level design challenges is to select the right protection for the IC. So a board designer, a system designer goes and buys an off-the-shelf TI part, for example, and then is wondering, okay, what type of protection do I need? So there needs to be some understanding of the threshold voltages that are safe on the IC, and then select an external protection that will trigger before the destructive limit is reached. So for example, here, in this case, if the threshold voltage for the external clamp is actually too high, it looks good in the schematic, it looks good on the PCB, but all of the energy is going into the chip, and it's not actually doing its job to protect. So in that case, something like adding a resistor or some kind of impedance to direct the current, the primary protection is needed. So I'm going to just leave you with a thought, or as we get towards the end, a thought of what is a PCB and what is a system. And as we go to more and more integration, we're seeing that there's new types of system integration where there's three-dimensional boards, three-dimensional chips, multiple materials and different types of sensors embedded. So all of this is presenting itself as an interesting challenge for ESD protection. So in summary, and just a takeaway, I hope I've highlighted to you that ESD is pervasive and can damage ICs if not properly controlled. All pins on an IC need protection. And protection involves understanding of the higher current behavior in order to safely discharge. So this is an introduction. I'm hoping to, over lunch, to spark curiosity and bring you to the next level of understanding with this. There's lots more to look into, and lots of publications, organizations. In fact, the Bay Area ESD Forum, we meet about 4 times a year. It's a casual meetup to learn about some of the things that are going on. So thank you. But before I finish, I just want to highlight a little bit about the ESDA. So the ESDA, similar to, it's a professional organization. It would have similarities to IEEE, but on a smaller scale. Founded in 1982, it's a professional voluntary association dedicated to advancing the understanding of EOS and the theory and practice of electrostatic discharge. We have 16,000 members worldwide and lots of opportunities to learn and to give back. And then just to acknowledge the Education Committee Advisory Board. There's a bunch of us from across many different companies who've contributed to the education material that's included in this.